All right, so the paper I will present today is called Dynamic Faceted Search on Discovery-Driven Analysis. It covers a couple of aspects in related to faceted search. The first one, which I've taken the most notes for, and I will go through mostly through the notes rather than the paper for sake of simplicity, is the problem of ranking facets. So the problem statement is a repository of documents, basically a data set that has n facets, a query q, and two integers, k1 and k2. We want to select k1 facet sets, so sets as in facet groups, and the facet summary for each of them with up to k2 values that are the most interesting for the user. So we basically how to rank facets to guide users towards refining their search. That is the first problem that is addressed, and we will talk about in the first part. Later on, they also talk a bit about performance of facet counting, because when you do facet search, returning results that match the facets is only part of the problem. Counting facet values is also an expensive operation. So we talk a bit about what is the standard way of doing it, how Solar has done some performance optimization to improve the performance of facet counting. And then there's yet another performance optimization that is introduced in this paper. Cool. So let's start with the problem definition of with this problem of sorting facet. The easy and most common approach of ranking facet values is by the number of matches, like how many results in this result set match each facet. That is not necessarily the number of the number of matches doesn't necessarily correlate with what is most relevant to a particular search. So here we introduce a measure of interestingness. So basically how surprising or how interesting it is that the count value is different from an expected value. So basically the user will have, broadly speaking, we have some expectation to see for facet counts. And if the count is much higher than what we expect, then we would call that interesting. And it's probably something that we want to present to the user. So there are two parts here. One part is setting the expectation. There are different ways to define what is the expected number of hits of matches. And then there's a part of diving into a bit more detail of how we define how surprising it is that the count value is different, or what does interesting mean. So for one way of setting the expectation is natural expectation, which is they call this natural expectation. It is what the user would expect if they have no knowledge about the data set that they're searching. So the easiest thing that you could expect is you would expect all documents in the repository to be uniformly distributed across each facet value, and all facet values are independent of each other, which roughly means if a result set has, you make a query that has 100 results, and for these 100 results we have 5 different brands, then the expectation would be to have 20 results per brand, so they would be uniformly distributed. Just to see what would be interesting by this definition, if you search in a patent repository where IBM, for example, owns a very large percentage of patents, if you search for something in the patent repository, IBM is likely to be interesting in most searches because IBM owns more patents than others. But IBM would still come up as, like, in all searches, they would have more than average. So they would probably be the most interesting one in all searches. The second, and the one that they've spent more effort developing and that was evaluated as better in this case, of the better way of setting the expectation, is the navigational. So it starts by the navigational way of setting the expectation starts by setting the expectation to the distribution of facet values that facet values have in the data set as a whole. So we expect facet value counts to have the same distribution on our query that they have in the data set as a whole. So, for example, in the actually, let me go here because I've annotated things better here. In the original query, when the user just comes and makes the first search, for each facet, our expectation is defined by this formula. This is the count of facets divided by total number of documents times the number of results, number of documents for this query. So this first part is the percentage of documents that match a facet value in the whole data set. So how many facets were, what percentage of patents were issued by IBM in the whole data set in our IBM example, times the number of results. So if we have 100 results and 30% of patents are issued by IBM, we would expect 30 results in this data set to be IBM. Does it make sense? So we expect in the original query the facet distribution to be the same as the distribution in the whole data set. When the user issues a second query, this will explain why it's called navigational, by drilling into selecting a facet, we reset the expectation using the results from the previous query. So instead of when calculating the percentage, instead of taking the percentage of matching documents across the whole data set, we take the percentage of matching documents in that previous query. So you make a search, you select a facet. Now we see before you selected the facet, what was the facet value? What was the percentage of documents that matched this specific value? Multiply that by the total number of results in the new, the number of results in the new query, and that will give us the expected number of matching documents for that facet. So using this expectation for a query on XML in the patent repository again, a startup that has only 5 patents, but all of them are on XML, will be more interesting than IBM. We would have a high expectation of patents for IBM initially because they have a lot of patents, and a low for this startup. But we're searching on XML, then this startup has a higher percentage than expected, so they will be a more interesting facet. Does this make sense? So the first one was the natural one, just expected always in all queries. We are surprised if anything has more than than a uniform distribution. And in the navigational methods, someone that matches more on this query than they do on the whole data set, then they are probably the more interesting facet to show. Is that clear?
Yeah, just to clarify, in this XML example, what is the first query and what is the second one?
In this example here, I'm talking only about the very first query. So you just make a first query on XML. If this startup that has only 5 patents, your expectation would be that you see like close to 0 results for them. But if your query has 100 results, and 5 of them are from this startup that has 5 patents, that 5% are coming from this startup, but you would expect to see way less than 5% because they have like 0.1% of all patents in the data set. So you say, okay, this is surprising, so these are probably worth showing. Does it make sense? When we start from the very first query, the expectation is not related to any previous query. The expectation is, so I expect for this startup, I expect the facet count. To set my expectation for the facet count, I would say, okay, this result set has 100. I'm getting 100 results for XML, 100 papers. This startup has 0.1% of papers across the whole data set. So I would expect one or less than one, not even one result to come from this startup. But since I'm getting 5, so 5% of the whole data, of the whole result set, then I say, well, this is surprising because they have a small percentage across the data set, but they have a high percentage in this result set. So I would consider this interesting.
Cool. Thanks.
When then, if you go on and you select another facet, the only thing that changes is that when we create that percentage expectation, we use the number of matches from the previous query, not from the whole data set anymore. But it's still the same principle, that if it matched 2% of results before, in my original query, now I selected another facet, and this increased to 10%, then now this becomes interesting. Like, for example, Nike had 2% of the results. I selected color blue, and then there were 10% of Nike results, and maybe Nike is good for this color. Oh.
Yeah, I just realized that this second query is not like you type a different query, but you just select one facet.
Yeah, exactly. It's just a subsequent facet selection.
Cool.
So just one question. I don't know, like, are there details about the implementation? So this means we should maintain kind of, let's say, previous states if you want to implement this. Did you have thought about
this? For this you'd have to maintain previous states or have the client send it back. But yeah, you would need to know what was the previous one. A simpler implementation of this would be to ignore this navigational part and just always use how many they have in the original one. But this is a more, this helps reinform your decision, like an additional signal. So they've used this method when evaluating. Cool. And then interestingness. So now, like, how do we quantify how surprised we are? Because like I said some examples, but how to quantify it? And I just copy pasted because from the paper, because this is a pretty clear explanation in my opinion. So support that a certain facet value occurs in R out of capital R documents in the whole repository. Repository here is the whole data set. And in Q out of capital Q documents in the output of a certain query. So this is the number of results, and this is the number of results that match a facet. This is data set size, and then number of items that match it on that data set. Now we also suppose that the percentage in the result set is greater than the percentage in the whole of matching items in the whole data set. Then the interestingness of that facet value would be the probability that in a random sample of size Q, size of our result set, there will be at least small q documents with that facet value. So this is basically the p-value. Gives us the probability of obtaining at least this many results that match the facet under the while given the fact that we know what percentage of items match it across the whole data set.
Isn't it affinity engine, Alex? It looks very similar.
Yeah, really close.
All right, but in this case, it's applied to only to facet. Yeah, so you have it on on a query basis, like how. Actually, yeah, it makes sense. If you pick a facet in the affinity engine to boost the results, that will probably also be a facet worth showing up to select. The thing with this is that we don't need to have any clickstream data because we're working only on counts, like how many facets are in the whole data set and how many match this document. And there's, if we check the paper, they have the formula for that expectation. And then they say, of course, a similar hypothesis can be derived when the number of returned results is less than the average. In that case, it would be uninteresting because chances that we get them randomly, if chances that you get an IBM paper randomly in a random sampling of the papers pool are very high. So if you get just like a few of them, that's not very interesting. You could have gotten them by chance. And they talk a bit about how they've played, like here we approximate p-values using normal distribution or the Poisson distribution for easier calculation. However, like whether you use sampling with replacement, without replacement, doesn't matter too much. Here we're just trying to get like an approximate score of how strange, how weird it is, that interesting it is that we get that many matches. All right. And then now so this is how to sort single facet values. Now there's also the question of how do we score a whole facet group. And the first idea that they mention is that you could use a similar approach where you see the distribution of facet values of a facet group within the whole data set, and then you try to figure out from the distribution that you get on the count, what are the chances that you get this distribution? So how that could be at least this skewed if you do random sampling. However, there are a few problems with that approach. One is that if you have one very interesting facet and a lot of uninteresting facet values within one facet group, you could end up ranking the whole facet group as not interesting, even though it has like a couple of very interesting options to select. Like you get, for example, you search for shoes, you get 2 or 3 good brands, Nike, Adidas, I don't know what. And then you get some other brands that are not related to shoes. We could, if we just use the same approach across the whole facet group, we could end up determining the whole brand group as irrelevant. So what they do instead is a simpler approach. They start by considering the p-values of only the k most interesting values in F. F is the facet group. And suppose we sort these p-values, p1, p2, pk. Replace them by something that turns them into increasing order. So by setting S as minus log of pi. So they become S1 is greater than S2, greater than Sk. So that, you know, a high score here would mean interesting, because for p-values, if the p-value is low, so that the chances that you get them randomly are low, then that makes it interesting. We just invert them to make sure that a high score means that this is an interesting facet value, and we've taken just the k most interesting ones. And finally, compute a final score by a weighted average of these. Not average, just a weighted sum of these S scores. And the weights are assigned with 3 different strategies here. Max weight is just that it sets the weight to 1 for the first facet value and 0 for the rest, which is what we do now when sorting by relevance, although our definition of relevance has nothing to do with distribution. So just basically the facet group is as interesting as its most interesting facet value. There's average weight, which just uses an equal weight for all facet values within a group. And there's hybrid weight, which just takes an average of max weight and average weight. So you get the how interesting the first one is, then you get how interesting all of them are, and then average these 2 results together. Both of these 2 are more the most successful one, and they show that it's even better for relatively small k. So the interestingness of a whole facet group is determined by how interesting its top facet values are, not all of them. Because in the search results set, you may have like 20 good results and then maybe 100 irrelevant results.
How do you choose k?
I don't think they had any, unless I missed it, I don't think they had any good heuristic for this. It's just a small number of matching facets. Like it could be a hard-coded 3, 4, or like 10% of facet values within the group, something like that. It's just the top value, but they didn't have any method for for choosing K. Does it make sense so far? Just the ranking part. This is it about the ranking. So later on they go. You can read the paper to see how they do the evaluation. They just come to the end result is that the conclusion that this navigational way of setting the expectation is the best, and these two ways of averaging when sorting facet groups, these two perform similarly, and they're both okay. Cool. Then for the next part, I wanted to talk a bit about the implementation and of facet counting, and how it's done in Solr, and then an additional performance improvement that is suggested here. So basically, they say to support faceted search over an inverted index, you map every token to and every facet value pair to an index term, and the system first identifies all the matching documents, then computes the count on each facet value over the set of matching documents, and then finally selects a subset of facet values and the corresponding counts. Because we may not, this is in the case, right now we show all facet values. This is just, we've already hit some cases where we have so many facet values that we don't want to show all of them, and it makes the response huge. So the last step is that you pick the top ones. And they focus on this second part of computing the count of each facet value and how this can be computationally expensive. Simple implementation to do this is that you keep, in addition to this inverted index, you also have a forward index, which is for each document, you map all the facet value pairs. So you keep a list of facet value pairs where the key is the document ID and the facet value pairs of that document are the values. At runtime, as you're going over the results in the inverted index, you can get all the facet key value pairs for each matching document, and then update your count with keep track of facet counts in a hash map. Solr uses another implementation where they take advantage of the inverted index also for counting facets. So Solr is built on top of the scene, and instead of keeping this, going through all the documents that match the search, for each document get the facet key value pairs and then update the hash map with the counts. Instead of that, they just have facet key value pairs like we also do in the inverted index. So facet key facet value is a key in the inverted index, and all the documents that have it form a posting list for that facet key value pair. And then for so you basically when you make a query, you iterate not in the query. You don't have only the tokens, but you also have the facet. And to speed this up, it says that Solr caches the posting list of a facet value to represent a bit set in one of two ways. So basically, the posting list for a facet key value pair is a bitmap of all the documents, which is like 1 if the document has a facet key value, 0 if it doesn't have it. And this bitmap is stored in one of two ways. If the bit set is dense, it's just a normal bitmap. Otherwise, it's a hash map of document IDs. They here, hang on, there was another.
One question that I don't really get, maybe that's a minor. What it means in parentheses, it was saying singleton solver or something like that. I'm not getting that. You managed to digest? Oh, computers that count on each facet value, singletons only, over
For each key value,
the
computes the
queue.
count of on each facet
Like
value.
left colon.
Yeah, I think it just means that you have. Yeah, I'm not sure what they mean actually by singletons only. It's just for each, each unique facet value pair.
Okay.
I guess. So one first implementation that they do over Solr. So yeah, this is what Solr does. So they have a bitmap of document IDs, and they just intersect. One improvement that they do here is that they compress that bitmap. So you have the posting list of a facet key value pair represented as a bitmap, and they compress it using this word-aligned hybrid code. The way this works, I will just write here, is that if you have, if this is your bitmap, you break it down into groups of 31. I will just break it down into smaller groups right now. You take the bitmap, you break it down into sequences of a fixed size. Then you have an additional bit in front of each row. If so, yeah, let's say this is the bitmap that I want to represent. If the first one is contains both ones, for each of these sequences, if the sequence contains both ones and zeros, then you just put a 0 in front to say that this is a literal, and then just copy the whole thing. So we will do the same here because it's a sequence that contains both ones and zeros. Now, when you have a sequence of only zeros, what you say is you put a 1, meaning that this is a repetitive sequence. The repetition, then you have another bit for the repetition pattern, so it's 0. Here now we have a bunch of zeros, not a bunch of ones. And you use the rest of the bits to represent how many following rows are all zeros. So we have 1, 2, 3, 4. We have 4 rows that are all zeros. So the next would be something like this. These bits just say now you have 4 rows of all zeros. So we compressed this bitmap into this one. Basically, for any row that has both ones and zeros, you just keep it as it is, and you add an extra bit. For repetitive sequences, you say, okay, now I have a sequence with this many rows of all zeros. If these were all ones, then this would be like this. Does that make sense? The nice thing about this compression is that you can do bitwise operations without decompressing. So if I want to do a bitwise OR for the parts that are literals, you just do it normally because they are not compressed. And for these, I know that I'm doing a bitwise OR on this bit, and I have to repeat that on all of those sequences. So you can do bitwise operations without having to decompress.
It's very cool.
So this is one additional optimization they do on top of Solr, and then there's another one that when they build these bitset trees. Bitset trees. So here's an example of how they're built with when the whole data set size is 5. So for each facet value, unique facet value, they have a bitmap that represents the posting list for that facet. Then they create some groups. So 3 here is a fan out parameter, so like some parameter for building this tree. So they group all the facet values into groups of 3. Then for each layer, they create additional nodes on top. So the value here is a bitwise OR of each of these posting lists. So basically, what this tells you is If you have any ones here, it means that there are some facets under this branch that have that match a document. So you group the facet, you take the posting list of each, and then for each facet group, you create an additional layer on the tree where you take the bitwise OR on each. And now the reason they do this is because as they're counting facets, so they want to do this intersection of the posting list they get from the query with the facet, with the selected facets. They don't have to intersect with facets where they know that they will get no matches. So they will go, if you have something here of all zeros, it means that nothing under this whole tree has any matches. So you can just continue to the next one. Does that make sense? We can also go into a bit more detail too, like the example that I mentioned in the paper.
Sorry, how this information is being used later? Not sure I follow that part. Is this for approximation of facet counts or what?
Yes, so you want to intersect, for someone, let's say, searching for shoes and is selecting brand Nike. You want to get the counts for all facets.
Okay.
So let's say a facet F has only 6 values, and that are enumerated by F1, F2, F3. These are like the 6 different brands, for example.
Okay.
And the posting list is equal to 5. We have just 5 documents overall.
Okay.
Now we have the list of all. We have the list of all documents that match the search query. Now we want to compute facet counts. So we take the bit set that represents documents that match the query, the bitmap, and do a bitwise AND with this part. If we get a match, if any bit ends up being 1, it means that in this result set we have some of these facets under this branch. Otherwise, if these are if we have a bitmap of 1, 0, 0, 0, 1 as the results from the query,
okay,
it means, and we do a bitwise AND with this, we get 0. It means that none of our results have any of the F1, F2, F3 facets, so we don't need to bother updating counts for F1, F2, F3.
Okay.
We do the same here, and we see, okay, now we have a match, so we should look here. And we update the, we have, I said our result set was 1, 0, 0, 0, 1. The bitwise AND is non-zero, so that means that in our result set, we have some facets that we find under this branch. We intersect them again. So it's okay, we have F4, so we update the count for F4. We intersect with this, we get nothing. We intersect with this, okay, we update the count for F6. What Solr would do is that for every facet, it would intersect every facet with the result set to get the number of the count for every facet. So Solr would end up doing 6 intersections to get facet counts here. But we managed it with 5, because we did 1 here, decided not to get into this branch. Then we did 1 more here, decided to get into this branch, and then 3, 4, 5. Does it make sense?
Okay. Yeah. I think ultimately I need to read the paper myself.
Yeah, sorry,
I
skipped. I actually skipped a part. So when we say how Solr does it, so Solr will have posting list for each key facet value pair.
Okay.
So when you get a query for each facet key facet value, it will intersect the results from that facet key facet value with the query results to get the counts that match both the query and the facet. So it's doing for every facet key value pair, it's doing an additional, it's doing an intersection in the inverted index to get the count for that facet key value pair.
Okay. So
and
this is the part that sorry, this is the part that you mentioned for dense ones, it maintains a bitmap, and for the sparse ones, it maintains a hash map.
Exactly.
Right?
Yes.
Okay. Okay.
And again, you know, each of those is in the end just a posting list. And this optimization is so that it doesn't need to do the intersection for every single facet, but instead it just does it for, you know, the ones that, you know, it does some partial lookup in front. Do I have anything under this branch? Yes, no, then go to the other branch. There are some cases when this ends up being slower. For example, if we have something like 0, 0, 1, 0, 0, so the one matching both sides, then in addition to doing 6 intersections to get counts for 6 facet values, you also do this extra 2. And one optimization that they do is that they try to make these groupings such that they share as few bits as possible. And there are only heuristics to achieve that. There is no, you know, solving the problem optimally is NP hard.
Okay. Does this tree always have 2 layers? Like,
no. So normally you will have many more. So you will have, like, if you have 100 facet values, you will group
have
them
100 leaves.
You will have, well, if you have, let's say, if you have 12 facet values, then you will have four leaves. For every 3 leaves, you group and you build one on top, and then you continue doing that until until you have, you know, you don't have any more 3 to the group together, because the number reduces on every layer.
Okay, cool.
Yeah, this is the part that is interesting, and I would encourage especially Narek and George to, I will send you the exact section, because it's actually very quite easy to understand. I just don't have the time to explain in more detail. But basically, Solr does facet count. The takeaway is that Solr does facet counting in the inverted index. They just have a posting list for each facet key value pair. But then for each facet key value pair, they need to intersect it with the result set. They introduce an optimization when, like, they try to figure out which ones will have no matches at all beforehand and only do it with some of them, but it's still an intersection on the inverted index, which we've also had in the very first implementation, and it is pretty fast. One that this doesn't consider at all is that if you use the same query that you got from the user to discover facets and to get the result set, then you end up with this problem where if the query is shoes and selected facet brand is Nike, then all the results from your query will have brand Nike. So you will have no counts for any other brands. So the query, like you need to intersect, the query that you need to make to count facets is different from the one that you have to get results. Because to count brand, you need the counts of everything that matches all the other constraints besides the brand constraints. And to count size, you want counts for results that match all the other constraints besides the size constraint, because you want to see also the other sizes. And there's an article by LinkedIn, which I also shared, and basically their solution, so they use Galean, which is an in-house search solution also on top of Lucene. So they have some similar constraints when it comes to indexing. Their solution is basically to build 2 queries and send them to their search index in parallel. They build one query that has, so like, let's say you're searching for engineers from Google, Facebook, or LinkedIn. They have one query that says engineer from one of these facets, Google, Facebook, LinkedIn, which gives you the results. Then they send another query for counting facets, which just says engineer, but all of these constraints are optional. The company constraints. So they basically send 2 parallel queries, one to count facets, and then they reformulate it, send another one to get the results, try to do these in parallel. What we do is different. So we actually do the counting and the query results in one pass, and we take care of this problem. I think I was hoping that we would actually have time to compare these approaches a bit, but that could be something that we follow up with later, maybe in a backend team meeting or something like that, because there are some interesting trade-offs, which we unfortunately don't have time to discuss now, but between the way that we implement this. So all of these ideas that are out there with how Solr does this, like except for these bitmap compression techniques, all of the other approaches have been floating around in our implementation. So George, I remember, mentioned a while ago, I don't know if we have that in the product or not at the moment, if we're just doing that forward index approach. But I remember George having this idea of having one query result iterator and then one facet counting iterator, which removes, creates multiple iterators to count results for each of the different facet groups. And yeah, I think it would be interesting to consult, to get this insight on how this is done in other search engines. It's interesting that Solr and Lucene don't deal with this problem of facet counting when you have selected a brand that you want to also show facet brands. They leave that. They basically consider that business logic, and it's up to the user of the search index to reformulate the query and say how they want to count facets and how they want to get results. The solution that within a single query does both of these. And for further improvements for us are these bitmap compression techniques that could both this word-aligned hybrid and then this tree approach, which lets you basically do the intersection without actually going through all of the items. Yeah,